Finishing up 2.3, example 13. There's going to be two of them. I'm going to do the first one, and I'm going to kind of let you play around with the second one because they're very similar. This type of question makes a fantastic, wonderful multiple choice question. Don't they all? Don't they all? I know. This makes a good one, though, too, also. I'm not lying. This is a piecewise function, and we've worked with them enough this year, but notice there's some missing values, A and B. And when we saw a problem like this previously in the year, we were trying to find the values of A and B so that the function was what? Continuous, right? And we used the three-step definition of continuity. We found the limit from the left, the limit from the right, and the function value, and we forced all three to be equal. And that was enough to give us two equations with two unknowns. In this problem, we're trying to find the values of A and B so that the function is differentiable everywhere. Now, to be differentiable, yeah, it has to be continuous, right? But continuous how? Smoothly continuous, right? So it has to be continuous and smoothly connected, or smoothly continuous, right? All right, so we could use the alternate form for that because remember the alternate form is designed, it's invented to handle the continuity and the slope aspect. But because we have the power rule now, there's a lot faster way. Here's what we're going to do. We're going to set the y, we're going to force the y values to equal each other, and we're going to then force the slopes to equal each other. Now, where are we going to do that? Well, let's see where it's needed. We want to make it differentiable for all x. To the left of one, we have a line, and to the right of one, we have a parabola. Lines and parabolas and cubics and any polynomial, they are differentiable for all real numbers. Okay? They're smooth, continuous everywhere. So the only place where it might not be connected or smoothly connected is at 1, where it changes. So that's really all we need to check. So let's go ahead and force the y values to equal each other at x equals 1. This would be the continuity aspect. We're forcing it to be continuous, just like before. The limit from the left of 1 is what, by direct substitution? 2, good. Now the limit from the right of 1 happens to also be the function value. So by direct substitution for x, we get a plus b. And we will force those to equal each other, which forces the graph to be continuous there. Now in the past, that was enough right there to give us two equations with two unknowns. Here we have two unknowns, yeah, but how many equations? 1. So we always need as many equations as we have unknowns. So we need one more equation. Now doing that and that alone is not going to be enough. And let's see what we're actually doing before we get to the next part. We basically have a line, 3 minus x. We know what that looks like, right? Let's go ahead and sketch that. Here's 1. We said the limit from the left was 2, so it stops right here at 2 with an open circle, and it has a slope of -1. Let me get this stuff out of the way. You go over there. Okay. So we're coming in with the slope of -1. What we're trying to do is find the values of a and b for this parabola so that it's going to be connected and smoothly connected. So the parabola could fill in that void and be continuous, but it could open up. That would be connected, but would it be smoothly connected? No. So what we're trying to accomplish then is to make it go from a line to a parabola such that if that 1 was not marked there and you didn't know the x value where the transition was made, you wouldn't really be able to go up there and pinpoint exactly the x value where it changed from line to parabola, right? That's our goal. Can it go up? Could the parabola go up? Maybe. Maybe it could go up. I know that this is certainly a possibility, right? So it could be that a could be a negative number. It could go up, but look what it would look like if it went up. The line is fixed, so maybe the parabola would have to do something like that. We would have to pick up on a part of a parabola that was still decreasing and still see the vertex. So yeah, it could work like that. We're not quite sure. How are we going to know for sure? We're going to use math, right? So we just made sure it was connected, but as I already showed you, it could be connected but not continuous. So here's where the slopes come in. What we're going to do is find a piecewise derivative function. And you can do it for a piecewise function. You just have to do the same thing you do for a regular function, but you just do it in pieces. So, to the left of 1, if the function is 3 minus x, what is the derivative of 3 minus x? Negative 1. 0 minus 1. Right? Because 3 minus x is a line with the slope of negative 1 everywhere. Now notice to the right of 1, I'm not going to put greater than or equal to 1. Because as soon as I say f prime at 1 equals 1, I'm claiming the derivative exists. And I'm trying to find the values of a and b to make it exist there. I'm not sure if those a and b values actually do exist. So I'm just going to say greater than 1. And by the power rule, what would be the derivative of ax squared plus bx? 2a x to the first plus b. Yeah. Now, once you have the piecewise derivative, you're going to do the exact same thing we did over here for the y values, but you're going to do it for f prime. You're going to plug in from the right and left for x. Now, from the left, it's negative 1 everywhere, right? Nothing to plug into. Plug in a 1 from the right, and we get 2a plus b. And by forcing those to equal each other, we are now forcing the slopes to be the same on both sides. Well, now we have two equations with two unknowns, and we can solve them simultaneously. So if you want to rewrite it, a plus b equals 2, and 2a plus b equals negative 1. And now you have your choice of solving that however you want to. Substitution, linear combination, Cramer's rule. Which one? Yeah. There's another thing you could do. Some of y'all just like having the signs opposite, but if you just want to go minus, because you notice that the b's are the same sign, you could just go top minus the bottom. So like mentally distribute the negative. It's a little bit faster, but whatever you want to do. A minus 2a is negative a, right? B minus b is 0. And then 2 minus negative 1 is really 2 plus 1, which is 3. That saves you from having to actually go through and rewrite it. And of course, then a would equal negative 3. Now, although we did point out that the parabola could open up, it turns out that the winning parabola has an a value that's negative, so it's going to be the one that opens what? Down. Yeah, but of course, it could have opened up. We would have just had to have shifted the parabola over far enough to make it happen. All right, so now that we have one of the values, we can plug it back into either one of the two, which I like the top one. So we get negative 3 plus b equals 2. And of course, then b would equal 5. And once you have the values of a and b, that's all the question asks you to do. You're done. On a free response, you would just find them. If you write below the a equals negative 3, it's okay to box it. If not, do it off to the side. And then the bottom line is your answer. On the test, I might have you do something with a and b once you find them. Like I might say, if a and b are the values that make it differentiable, what is a times b? And of course, then the answer would be 15, right? Or I could say, what's a plus b? And of course, the answer would be 2. So what that does is it kind of prevents you from eliminating answer choices if you think, a has to be negative possibly. You're not sure if a is negative. And it's easier for me to type up just one number instead of multiple. So, all right. So I'm guessing that it's going to look something like this purple situation here. And we made it connect smoothly. All right. You ready to try one on your own? Yes. Go ahead, Mr. Carr. Uh-huh. That's a really good question. If this were a free response, which it will not be on your test, at this point, since it's not specifically asking for the three-step definition of continuity, you could just show 2 equals a plus b. But I would expect some kind of label that is looking at either the continuity at 1 or the y values at 1, and same thing over here with the slopes. So if you label it the way I did it, that's fine. I would probably ask it in a such a way, if it were a free response, like part A, find the continuity of the function of x equals 1, use a 3-step definition. And then you'd have to like show the limit as x goes to 1 from the left, if it says that. These type of questions make really, really, really good multiple choice questions simply because you can skip a lot of the formalities of the notation and get to the equations and the answers pretty quickly. So that's how I'm going to ask it. That's usually how College Board asks it as well. Good question, though. I'm glad you bring up the notation all the time because I really did not use the limit notation very well here. So do the same thing on example 14. Pretend it's a free response. Find the values of A and B here that you make it differentiable for all x. We're going from a parabola to a line instead of a line to a parabola. So the only value of x where it really should matter is what? -1. So do kind of the very same thing that we did before. While you're doing it algebraically, I'm going to go ahead and sketch what the graph might look like. And then we'll meet back here in a few minutes. When you have your equations equal to each other, remember the x should not be in there because you've already plugged in when you found the limits from both sides. So it should just be a's and b's at this point, or c's and d's, whatever the variables that are given. There should be no x's in it.
I don't get what's my second y?
Let's see, your slope equation should be, what's the derivative of bx squared minus 3? It's 2bx to the first plus 0.
Right, square multiplied by square.
No, this is just the power rule.
Oh, okay.
Right, the power rule. And now
that'll give me my second one.
Well, right, but so you have the wrong f prime equation.
Yeah, I'll do this one.
B and A are just constant, so just.
Wait, I did both of them wrong?
Yeah. Find the derivative when you're doing the slopes. Find the derivative f prime of x first, x, and then do the limit from the left and limit from the right. Yeah, you're right there. Yeah, keep going. A is, yeah, that's it. Now find the other one. Yeah, I think one of them's negative. Yeah.
Am I good or is I'm on the left?
A should be 3. Yeah, y'all both got A, and then B. This B is right. That B, you're off by a negative. Oh, for the derivative? Yeah, you should still have an x in there. The derivative is going to be 2bx to the first plus 0, right? And the bottom derivative is just a, because b is a constant, it goes to 0. Right, so it's just a. So now when you plug in your -1, you get not 2b, but negative 2b equals just a. Negative 2b just equals a. Make sure you find f prime of x before you plug in for your slopes. How are you getting f prime? How are you getting your f prime equation? Oh, we're on the wrong one. Okay, that makes more sense. Yeah. Okay, yeah, that's good. But this is -1 still, right?
Oh, yeah.
So when you plug in, that'll be negative 2b, not 2b. So negative 2b equals a. Because there's nothing to plug in there. There's no x. That's right.
I have 2bx there, but down below I put negative 2b.
Well, because now you're plugging in, right? So you're plugging in for x, so you get negative 2b, and here there's nothing to plug into. Dun-dun-dun, dun-dun-dun. Yes, good. You got them both.
When I plug in the -1?
Yes, yeah. You shouldn't have x's there when you're setting them equal. No, but the 3 is gone too. Right? What's the derivative of bx squared? B is a constant. It would be 2bx to the first. Okay. What's the derivative of any constant? Yeah. Good. You got A. Good. Now you just need to find. Is that the B you found? Oh, that's not the right B. Yeah, but that's the right A. That's the right B. Close. Your B is so close. Well, these are both negative ones. I think that's maybe where the problem is.
I'm not doing it right. Don't look at the top part.
Okay.
I'm pretty sure I got A right.
Yeah, A is 3. Yeah. Because what's your other equation? What are your 2 equations?
And then I was doing it, I did it somewhere else, and then I didn't do it the right way, so I messed up and I wrote it wrong.
So B minus 3 should equal negative A plus B. So you set this equal to that.
Okay.
You have to force those y values to be equal. All right, let's look to see graphically, there you go, what we're doing. We have variables now in both of them. Good discussion still happening. That's good. Good, I like that. I'll give you another minute because this is good. Y'all are talking about math, trying to troubleshoot. No, the derivative, is that a B? Yeah, you never took the derivative. What would be the derivative of bx squared? It would be 2b, that's multiply, right, times x to the first, right? And then what's the derivative of negative 3? It's a constant. It goes away. It's a constant. And then on the bottom, this is a line, ax plus b. What's the slope of a line everywhere? Well, no, it's a constant, but it's always, this is like your mx plus b. And so the derivative of any line is just the coefficient of x, so it's just a. Just a. That's the slope of that line. All right, you ready to kind of go over it? Graphically, we have a parabola that has a fixed y-intercept of negative 3, and it has to smoothly transition connectedly into a line with an unknown slope. So to get a y-intercept of 3, I would either have to have the blue parabola coming in from the top, and then at negative 1, it would have to switch into a line going down. And notice I do the dotted line here. That would be kind of the parabola continuing. Or I would have a parabola coming in from the bottom, and right there at negative 1, turning into a line smoothly. And, of course, that parabola would have a negative intercept if I kept going. But this is what's important. Notice that if B is positive, my parabola is going to open up, yeah? And if B is negative, my parabola is going to open down. That coefficient of x squared ends up being the y-intercept of my line. So if my parabola opens up, then my y-intercept of my line has to be what? Positive or negative? In other words, if B is positive, my parabola opens up, but then my line has a positive y-intercept. Is it possible to draw this blue parabola opening up, getting to a y-intercept of negative 3, and then having the line have a positive y-intercept? No. So the blue situation up here is not what we're looking for. To have a negative B value then means for the parabola to open down, and then my line would have a negative y-intercept, and that's what we want. So it's this dark blue or dark plum graph that we want. And how could that be helpful if you just think about it like that without doing any math? Well, you know B has to be a negative number. And then the line has to have a positive slope, so A has to be a what number? A positive. And if you have choices that have A's and B's, because some of the choices say A equals this, B equals that, and there's 5 choices, you can eliminate some of the answer choices and maybe even kind of approximate the right answer. But we're going to do it the right way. The y values, forcing it to be continuous, just like before. Limit from the left is the same as the function value. You need to plug in your negative 1 there, right, and you get B minus 3. That's the limit from the left. That's the function value. You need to force it to equal the limit from the right of negative 1, which is negative A plus B. Now, in this case, you can stop, but what do you notice about this equation? Yeah, if you look at it and try to clean it up a little bit, your B's will cancel, and that's kind of neat because now you got negative 3 equals negative A, which means A equals 3. So you can actually find one of those without using a system of equations. But we still need to find b, and it doesn't help to plug it back into our original equation, right? Because it's going to cancel out. So that's where we need the slopes. So f prime, and this is where some people are still faltering. Just think of it as two power rules. A and b are constant. So the derivative of bx squared is 2 times b, there's your coefficient, times x to the 2 minus 1, which is 1. And of course, the derivative of a constant like -3 goes to 0. So that's to the left of -1. A line has a constant slope of a. Or you can use the power rule. It still becomes a. So that is a constant to the right of -1. Once you have your derivative function, now you can plug in your -1 from the left and right. So if you plug in a -1 to 2bx, you get -2b. And of course, there is no x value to plug into the right because the slope is always a. And you force those to equal each other. And now since we already know what a is, we can plug in. So -2b has to equal 3, which means b has to equal -3/2. And as we anticipated from the onset, b is a negative number, which forces my parabola to open downward and gives the line a negative y-intercept. And a is the slope of the line, which is +3. There you go. Kind of fun. So that'll be a multiple choice question on your test. All right, so that's the end of this section. The worksheet will be due on Thursday. When you come to class, we'll have a short little quiz too on Thursday. And then we're going to finish up a little bit with the product and quotient rule. We're going to start that right now, and then I'll kind of talk about the test a little bit. Okay? Sound like a deal? So if you want, while I'm turning this recording off, go ahead and download the notes for the next section for 2.4, the product and quotient rule.